All right, now today we're gonna be talking about energy cycles. Many types of chemical reactions. Some of them are more theoretical relevant. So first ionization energy, um, and then others that really do occur. All chemical reactions have an associated enthalpy change in reaction. Uh, in the higher level, those there are different types of delta H's depending on the reaction. There's a shit ton of them, but they all more or less take the same form, more or less. This is just review. Um, you'll study some new types of reactions in the HL syllabus. The first one is lattice enthalpy, which lattice enthalpy is the change in enthalpy associated with the separation of ions of 1 mole of an ionic solid, thereby forming gaseous ions. So basically, how much energy does it take to split the ions up? That's more or less what it's saying. How much energy does it take to split the ions up? Is what lattice enthalpy is stating. Some trends that you should know for lattice enthalpy is that atomic radius, the smaller the atomic, it's the same things as we talked about in topic 3. Smaller radius means higher electrostatic force, and higher charge means higher electrostatic force, assuming the radius is held constant or somewhat constant, i.e. going across a period means a stronger lattice enthalpy, whereas going up a group means a stronger lattice enthalpy. So there's that. The next one is hydration enthalpy, which is the change in enthalpy associated with 1 mole of gaseous ions dissolving in water to form a solution. Such reactions are always exothermic, as they result in the formation of ion dipole forces between the gaseous ions and the water. There's also a little bit there, an extra to do with to infinite dilution. I think it's hydration enthalpy is the enthalpy change associated with 1 mole of gaseous ions dissolving in water to infinite dilution. Is I think what is formally quoted here. But similar to the case of lattice enthalpies, the same trends apply. The next thing that you'll be introduced to is a energy cycle, which is more or less based on Hess's law. And hydration enthalpies are related by energy cycles to the enthalpy of solution. You can think of it as like adding vectors. You want to know the enthalpy change of that, but you know the enthalpy change of that, which that's just double. So the enthalpy change is just that, plus that, which yields that. Here is a shit ton of things. Now, when you do the Born-Haber cycles, which are just it's a special type of energy cycle for ionic compounds. It's basically like a loop, and there are the following reactions: sublimation, melting, vaporization, ionization, bond breaking, electron affinity, and formation. I know that's a lot. Now, keep in mind that some people, especially the IB, they tend to do covalent bond breaking and sublimation as atomization, which it's more or less the same thing. Which for some reason they do that. I don't know why, but let's do a worked example of one because I have nothing better to do. So, calculate the lattice. So we're going to do question 7 here. Give this a try for yourself when you're ready. When you're ready, I'll pause the video now, and I'll be going over the solution in 3, 2, 1. All right. So let's first draw ourselves a. What I like to do is first draw the very bottom, which is M G O S, and then what we can do is here. Now, the way you do a Born-Haber cycle is every step you go up, right? There should only be one change between each set of things. So, firstly, what I'm going to do is I'm going to let's label this delta HF, and we're going to do this as Mg plus half O2. Right? Now, let's change one thing and keep your states there. S back. This is S. This is gas. Now, first off, let's make everything gaseous. So let's do mg gas plus 1/2 O2 gas. Let's make everything gaseous. And that is delta H vap. Or some books would call this the atomization of magnesium. Then the next change, let's say the next change would be, okay, now that we have everything as a gas, why don't we ionize magnesium, right? So let's ionize, no, actually, you know what? I feel like breaking the oxygen double bond first, so delta H O, there's no real standard notation for that, Mg plus O, gas. And now let's ionize it, so IE1 plus 2, IE1 plus 2, I'm lazy, so I'll combine the ionization energies. You don't have to. Mg2 plus 2E plus O. And then lastly, you'll get, and lastly, note that I'm changing everything only here by one small step, one small increment only. And that's the idea of these Born-Haber cycles that you want to get into. Only change one small thing at a time, because you can measure the delta H with that. Now with the ionization energies, it's just easier for me to add them up together because, hey, they're similar, we can just group them together. But the idea here is that generally you first want to go to your standard state elements, then get everything gaseous, then make everything into ions. And that's generally the sort of process you want to follow here. And then similarly like what I did with ionization energy, we're going to do the same thing here with electron affinity 1 plus 2 to get Mg2 plus O2 minus here, which Mg2 plus O2 minus gas select delete that, and then we can go all the way down that cycle and delta H lat. And then you see to calculate the delta H of the lattice, all you have to do is go around the loop. Now, what if you wanted the electron affinity? Well, and so, okay, you would start from here, go down, and then climb your way up the loop. If you go down the loop, just remember the sign is negative, and if you go up the loop, it's positive. Is generally how I like to do things. But just keep your directions consistent. So, since the question asked for the delta H of the lattice, let's add those all up. Now, it was given in the question, so let's add them all up. So, it would be enthalpy of formation, so we have to go up, so 6O2 plus 602 plus 147 plus OO covalent bond enthalpy was 498 plus IE1 plus IE2 735 plus 1445 plus first electron affinity. Okay, no, it was just giving us the delta H for the reaction. So 612, which yields enthalpy value of 4039 kilojoules, right? Which yields us an enthalpy value of 4039 kilojoules. Now, note that you don't necessarily have to do this. You can more or less break it up into the algebraic approach of Hess's law that we would have done when we did Hess's law. You could break it up and do it sort of that algebraic way. However, I think for most people, this visual way is a bit more intuitive. And similarly, you don't have to do those Hess's law questions that algebraic way I taught you earlier, you could do it this way as well, and you would probably still get the same answer using an energy cycle. It really depends on what you like using. Um, I would be familiar with both for higher level because, they could test you on both. However, for standard level, it really just is a case of pick one and stick to it. And with that, I'd like to end the video. Thank you for watching. Don't forget to like and subscribe.